Good day and welcome back. This is our third and final installment investigating the calculus of vector valued functions. The previous two videos have focused almost solely on properties related to differentiation. In this video, what we'd like to do is kind of simply introduce the concept of integrating a vector valued function. And the nice thing is that we do essentially, I think, what one would expect. To differentiate a vector valued function, we differentiate it term by term. To integrate a vector valued function, we also integrate term by term. So if you wanted the definite integral of a vector valued function, you would have a vector which is made up of the definite integral of the first component, and then the definite integral of the second component, and lastly the definite integral of that third component. And before diving into a few examples, I want to note that similar to a comment related to differentiation, you should be familiar with the common integration formulas. That is, going back to your Calculus 2 notes, you should have a list of common anti-differentiation formulas, and you should also be very efficient and familiar with, I'll say at a minimum, the two basic techniques of substitution and integration by parts. So let's go ahead and dive right into an example. If we want to evaluate, in this case, an indefinite integral, the idea is the same. We just take the indefinite integral of each one of those component functions. So this would be the indefinite integral of cosine, the indefinite integral of 1 over t, and the indefinite integral of the square root of t. And each of these are kind of common formulas. The antiderivative of cosine is sine, and remember it's an indefinite integral, so we need to add a constant of integration. The antiderivative of 1 over t is the natural log of the absolute value of t. A common mistake would be not to include those absolute values, plus a constant of integration. But no, this is our second arbitrary constant of integration, so we could actually call these C1 and C2. And then our third indefinite integral, square root t, we can really think of square root t as being t to the 1/2, and recall that the antiderivative of t to the n is 1 over n plus 1 t to the n plus 1, as long as you do not end up dividing by 0. When we already took care of that n equals -1 case in the middle component. So in our case, n is 1/2, so we would have 1 over 3/2, or 2/3, t to the 3/2, plus a constant of integration. And it is perfectly acceptable to leave your answer in this form, but I'm going to go ahead and break it up. So we can think of this as being sine of t, natural log of t, 2/3 t to the 3/2. And what we are adding on to this is some arbitrary constant vector of integration, where that constant vector is really our C1, C2, and C3. And I really consider this just to be a good opportunity to go back and practice some of these common anti-differentiation formulas and techniques. And what I'd like to request that you do at this point is to pause the video, take, I'm going to say no more than 4 or 5 minutes hopefully, and integrate the following vector valued functions. Okay, so assuming that you've done so, and if not, really pause it and work through these, I assure you that you will get a lot more out of this if you think about it first and then view the video afterwards. And if we were meeting face to face, I'd be able to force you to do that, but I can only strongly encourage you through the screen. So in this case, let's go ahead and just throw that integral into each component. So we have the integral from 0 to 1, 4 over 1 plus t squared. The integral from 0 to 1 of 2t over 1 plus t squared, and the integral from 0 to 1 of e to the t. So essentially this is kind of a 3 for the price of 1 deal. 3 antiderivatives here for the price of 1 single problem. In the first integral, 4 is a constant, which you can pull in front. And when you are left integrating now just a 1 over 1 plus t squared, that is a common anti-differentiation formula. It is arctangent of t. And we're evaluating this from 0 to 1. And for this middle antiderivative, there's kind of two choices. I am perfectly okay with you telling me immediately what that antiderivative is from our experience. Or you could note that if u is 1 plus t squared, du is 2t dt. So you see we have a u in the denominator, the 2t dt is du. But if you look at that and you tell me that the antiderivative is natural log of the absolute value of 1 plus t squared, I am okay with that. Just make sure that you understand those details, and using substitutions is something that we will practice over and over again. And the antiderivative of e to the t is e to the t. So now we go ahead and we take care of this evaluation. So we have 4 arctangent of 1 minus 4 arctangent of 0, two common values. And as a reminder, we should always evaluate functions at these common values. Arctangent of 1 is equal to pi over 4, and arctangent of 0 is equal to 0. And what this would give us is 4 times pi over 4 is pi, minus 0 is 0. And just to remember, if we're saying arctangent of 1 equals something, this is equivalent to telling us, or asking us really, 1 is equal to tangent of what? And pi over 4 is where sine and cosine are equal. And moving to the middle component, we would have the natural log of 2 minus the natural log of 1. Natural log of 1 is a common value. It's equal to 0. So we are left with just an ln of 2. And in the third component, we have e to the 1 minus e to the 0. Or e to the 1 would just be e minus e to the 0, which is simply just 1. And something I really want to emphasize, and hopefully I'll do this over and over again as well, I'm always very willing to repeat myself, we need to make sure we are using good notation. And this is always true, but especially true with integrals. So including things like your dt in each step, making sure that we're putting equal signs, we're using angle brackets for vectors, and we're lining our work up vertically. If you're not doing these things, you are going to get notes from me on your homework assignments and potentially, points taken off, for things like not including equal signs, dt's, plus c's. Those are very important details in mathematics. And I know sometimes students can get a bit frustrated, understandably. No one likes to get points taken off. But my analogy is as follows. In an English class, we would never dare to turn in a paper completely void of punctuation and capitalization and sentence structure, though I've certainly tried, I think. And in a math class, the notation is equivalent to the punctuation and the grammar that one uses in an English class. So hopefully that puts it in a context that's understandable for you. Finally, here we have one example remaining. This is an indefinite integral of a vector valued function with just two components, an I component and a j component. And we could just as easily write this as the integral of secant squared t dt I plus the integral of 1 over 1 plus t squared j. And this is equivalent, recall from our discussion on vectors, to putting it in this form, first component, comma, second component. So first component I plus second component j. The antiderivative of secant squared, this is a common formula, that is tangent of t, plus The antiderivative of 1 over 1 plus t squared is a common formula as well, arctangent of t. And because this is an indefinite integral, we need a constant of integration. And our constant of integration, since we're dealing with vector-valued functions, would be a constant vector. So that completes the material that we wanted to cover related to the calculus of vector-valued functions. I will note, and you'll see this at the bottom of page 4, that there is an associated worksheet that you can find posted in Canvas, but I think all of the problems are extremely similar to what we've been discussing in the previous 2 sections. So you should be able to find examples related to all of them in the videos, but there'll also be solutions posted. So because of that, I'm not going to go over any of them specifically, but as always, if you have questions, do not hesitate to reach out to me. Drop me an email or stop by one of the virtual office hours. So stay tuned and take care.